In this video, we're going to be graphing exponential functions on the same coordinate plane. So we're going to begin with f of x equals 2 to the x and g of x equals 1/2 raised to the x. And we're going to be plugging in the numbers -3, oops, let's try that again, the highlighter, -3, -2, -1, 0, 1, 2, and 3. So when we do that, we have that 2 to the -3 power is 1 over 8, and to the -2 is 1/4, and then we have 1/2 and 1, 4, oops, 1, 2, 2, 4, and 8. And when we plug in our 1/2 to the x power, we get the value. See, if we take 1/2 and raise it to the -3, we get an 8, and 1/2 raised to the -2 is a 4, and then a 2, and a 1, and then a 1/2, and a 1/4, and a 1/8. And so what you might have noticed is that here our 1/2 to the x power is really just a 2 raised to the -x. As we see, our values are simply switching throughout. So really what we're seeing is a reflection, right? So g of x is a reflection of f of x across the y-axis. So let's go ahead and let's graph our f of x. And so here's our f of x. And let's go ahead and let's graph our g of x as well. And because it's a reflection, we see that our points line up in a really great reflection there. And they both have a common point of 0, 1. And so there is our g of x. So you're going to make a table of values and plug them in and then graph it. Now what you're going to notice here is that we actually have a graph that's increasing and a graph that is decreasing. So we refer to these as exponential growth and as exponential decay. F of x is an exponential, growth equation, and g of x is an exponential decay. So growth would be increasing from left to right, and decay would be decreasing from left to right. So let's talk a little bit more about exponential growth and decay and the domain and the range and the horizontal asymptote that it's included there. So an exponential equation, or function rather, is defined by f of x equals b raised to the x power, where b is greater than 0 and b does not equal 1, having the following properties. So if we have exponential growth, that means we're going to have some increasing here, and here our b value is going to be greater than the number 1. So that's going to be our exponential growth equation. Now if, however, our b value sits between 0 and 1, that is going to give us our exponential decay, which is why earlier our 2 to the x was a growth, but our 1/2 to the x power was a decay, because 1/2 is between 0 and 1. Our domain is going to be all real numbers. We're not going to have any restrictions as to what x can be. We do have a restriction to our y value. Notice here that our x-axis acts as a horizontal asymptote. So here our range is going to have to be from 0 up through infinity with this parent function. And our equation y equals 0, or the x-axis, is our horizontal asymptote. But also take note of this really great feature. Regardless if it's exponential growth or decay, the point 0, 1 is included in that graph, because if I take f of 0 and I'm taking b to the 0 power, regardless of what b is, that answer is going to be 1 every single time. And so that's a great property that we can use to help us. Another pretty cool thing is that, let's say we have the graphs 2 raised to the x and 5 raised to the x. Basically, we're saying that for every positive 1 unit change in x, so as we're increasing, like 1, 2, 3, as we do that, when we have something like 2 to the x, we're saying that it's going to be 2 times as great. And when we have something like 5 to the x, we're saying that it's going to be 5 times as great. So if this ended up being, let's say this equation right here was my f of x equation, or my 2 raised to the x, then my 5 raised to the x would actually end up coming in 5 times greater. So it would happen faster. And so that's another cool thing about exponential functions.